Hey, yesterday we were working on a problem. Yesterday, whenever this relevant in time for you, for me it was yesterday, but it was on the concept of work and how much work it takes to lift this solution, this chemical, this olive oil, up out of a conical tank. So what I want to do is I want to make sure that we have a chance to kind of wrap that one up or revisit it, kind of like a refresher. And so that's the purpose of this video for you, in order to help go back and cover that. So the situation, right? Check the closed captioning, subtext, whatever. It was, you have a conical tank, it's 10 feet tall, and you're gonna fill it up to 8 feet of depth with olive oil that has a density of 57 pounds per cubic foot. A cubic foot is actually about the size of a gallon. So if you think about a gallon of milk and how heavy a gallon of milk is, compare that to what 57 pounds would be if you're lifting up the same thing, okay, of olive oil. Now, one other thing is that this conical tank is created by revolving the line y equals 2x around the y-axis. So in our situation, in our problem here, we've got this revolution of the line y equals 2x around the problem. Let me zoom in a little bit. Now, around the y-axis. So there is this line of symmetry going right down the middle. The situation for us here is to figure out how to find the work that it takes to move the olive oil up. It's a 10-foot tall tank, but the oil itself is full to a depth of 8 feet. And so our information for this problem is to lift this amount of fluid up and over the top rim of the container. Work is our calculation. Work is a calculation that compares force to distance. If you multiply force measured in pounds by a distance measured in feet, you have an element of work. You have an element of movement, how much energy it takes. It's a different concept, but the amount of energy it takes to move that object a certain distance. In this case, all of this up and out. The information from here is we have a density calculation. So density that we're given is 57 pounds per cubic foot. And then we're gonna take that information and we're gonna multiply it by a volume amount. By doing that right there, we're setting up this structure of the volume of all of this liquid, all of this olive oil fluid is going to be lifted out. And if you have a certain volume of the fluid and every single cubic foot of that fluid is 57 pounds, it's a little multiplication problem. One thing that I have to make clear here, and this is in the setup for this problem from page 424 out of the green book, this is section 8.5, is that in order to consider your structure for work, the suggestion, the direction here is not to consider all of this all at once, but to actually consider it in terms of slices. When we talk about the volume that's contained in this object, it's set up through a concept of slices that are stacked, making little cylinder discs, and then adding up all of those cylinder discs. And the shorter, the flatter those cylinder discs become, as we approach a differential, the summation turns from being a sum sign into an integral sign. So we're gonna look at the disk, some random location in this cone of oil that's there, and we're gonna figure out what it's gonna take to move that disk, all of the oil in that disk, that cylinder, up and over to the top of the cylinder or the top of the cone and out. In order to do that, we have this density of the object. We also want to take the information that's given here. We want to calculate just the element of work for that one thing. So to calculate work, we need a force. Force is this value, but V in this case is not the amount of volume of the whole thing. It's just the changing amount of volume for this thing. So our V is going to have to be written a little bit differently. It's going to look like this one. We have our volume calculation. A volume in this situation is a cylinder structure, so it's going to be pi times r squared times height. Well, our cylinder that we've created, its radius is depending on this function that creates the side. But this function is like go over to an x value and go up to the y value. That's not going to draw us a radius. That's going to draw a height. So we have to solve this y equals 2x equation to get x equals 1/2. A y value. Give me a second. In that problem, that puts the radius right here of that one. It is the 1/2 y calculation. So I'm going to bring that down into our cylinder formula. R becomes 1/2 y. The height of this disk, it's the change in the y value. So this height right here, we're going to call delta y. And so we're going to replace h with that structure. That'll give us a volume calculation. It'll give us a volume of this object. And so we're able to then calculate the work that we have to do based upon just that disk, moving that disk up and out of the cone. Let me rewrite it. So delta V, all right, the volume is going to change depending on where we are, y height wise. So at a different y height, we have a different size disk, and therefore we have a different amount of work to move just that disk up and out of the cone. But we still have pi, we still have the radius, it's still squared, and delta y is our rest of the formula. This formula here for work, in some sense, that's like the overall amount of work to move the entire thing. But because our object is changing, because our object has different height values to it, the radius is going to be different depending on that value too. What we're going to do is we're going to say, let's calculate just the work to move this slice up and out. So we have our delta W, our changing amount of work. You move to a different y value, you get a different amount of work it takes to move that object up and out. So force is still the 57 pounds per cubic foot. We're going to multiply this amount by the volume at this slice. So the volume at this slice is this calculation. That would be, let's see if I can move this out of the way. Put you down there, put you down there. Okay. So we're going to multiply this density calculation that has a pounds are force, over cubic feet, multiplied by this formula right here. That way we can get cubic feet to cancel. Remember, this is a calculation of cubic feet. And so if we multiply our force, our density calculation, we're able to then, let's see, bring it over, times pi times 1/2 y quantity squared times delta y. This is cubic feet. So units analysis will help us understand. We're going to cross out feet cubed and be left with pounds. Pounds is a measure of force. How much force do you have to keep you on the ground versus floating up into space? Okay? So 57 pounds, half, multiply that by our expression from the previous quantity. This alone right here is force. The rest of the work equation is the distance we have to move this object up and out. So the value of here, maybe a little highlighter right here, this y value, in order to move the object up and over the edge of the rim, we have to go the rest of the y height. We went up a y height to get to the disk, to create the disk, but in order to move this like slice of oil, of all of the slices, in order to move it up and over the edge of the rim, we have to go the rest of the distance, a 10 minus y distance. Work as a calculation is a two-part process, force times distance. So if we take the force calculation, density times volume releases pounds, pounds are a force, and then we multiply by, I'm running out of room. I'm gonna write it here. It's gonna be an awful mess, but I'll go ahead and rewrite it cleanly down below. I'm just taking that 10 minus y and multiplying the force calculation. So then I'm gonna go down here. I have our force delta W. Rewrite it for cleanliness. Delta W equals 57 pounds per cubic foot times pi times 1 over 2y, that quantity is squared, times delta y. Then we're going to multiply further. This is also in cubic feet. Then we're going to multiply further by 10 minus y feet. So this is our distance. We have to move that slice up and over the edge. Now there's a bunch of different work calculations, but this essentially is the structure of it. Feet cubed and feet cubed cancel. So we have force times distance. Force times distance, our results are going to be in something called foot pounds. There's pounds on top, there's feet on top, so that's all good to go. If you look at all of the possible slices, here's one slice's information. If you look at all of the possible slices, there is a total of 8 feet of them that we have to add up. And if you add up all of them, you're going to get the work for each of those slices to be moved out of the conical tank. So integrating this, now this is where I want to make sure that if you were in the lecture where I set the problem up, it's over here on the board. In that lecture, we integrated volume. Don't integrate the volume, integrate the work. We're integrating each of the little slices, and so that creates this one. The total work is the summation of all of the little changing amounts of work. It's going to be the integral of 57, I'm gonna drop the units of information right now, times pi times 1/4 y squared times 10 minus y dy. This is the distance that the slice, like wherever they are in the continuum, has to be moved up out of the edge. This is the radius, it's squared, the 1/2 becomes 1/4 when you square it. 57 pi, 1/4. In fact, you could move all of these constants outside of the integral, and you might see that if you solve this problem. Last of all, we're integrating from 0 to 8. This is trying to bring back a little sense of finality to the work discussion. Instead of thinking about integrating volume, not in this problem. We're gonna let volume handle itself right here and right here. But we're gonna try to also take into consideration is work on its own is the slices that move the oil up and over the edge of the tank. And so I wanna make sure that I'm talking about the 10 minus y as a necessary component inside the formula. This is our setup for the work equation for that problem. Integrate it. When you integrate it, you should get 30,000, I erased it from yesterday, 30,561 foot-pounds. Call it our answer, call it done. Thanks for watching this video. Hope that it helps clear some things up for you, and feel free to comment and let's talk about it in class at a later time. Bye.